out all the algebra that you're supposed to know. This is a review. But depending on your background, some folks know it incredibly well. Some folks vaguely remember doing this back in high school. And as I'm doing this for the folks that vaguely remember doing this in high school, because this is real important stuff, because we're going to apply calculus to this, then set it equal to 0 and solve, and then when you solve, and it's an exponential or logarithmic equation, you got to know how to solve this stuff. So this is what I'm still in section 3.1, 3.2 on the algebra. Then I'm going to start section 3.1, 3.2 on the calculus and start focusing on the limit idea of these particular interesting functions, the exponential and the logarithm. So, last time we were working on some problems. We were doing the change of base formula, which is nothing but a formula really designed for your calculator these days to be able to, if you have a strange base on your log, log base 8 of 17, and you wanted to calculate this out as a decimal, well, the problem is there's no log base 8 button on your calculator, but you can change the base to either the natural log or the common log, which for both of those we have buttons on the calculator. And so the log base 8 of 17 is the log base 10 of 17 over the log base 10 of 8. Or you could have typed in, that's the same thing as the natural log of the original function, 17, over the natural log of the original base 8. Doesn't matter which way you type it in, you'll end up getting the same number. But I'm going to pick it up with part C here, solving equations. All right? That's where we're interested in and where we're going with this stuff. So, we can pass that out about 30 minutes or so. All right. So, here we go. Solving exponential equations. The first one, let's take a look at it. This is the basic type of exponential equations. Anytime you can write b raised to the m is equal to b raised to the n. If the bases are equal, that will imply that the exponents, m equals n. Now, this is the nice type when you get nice answers with exponents, because the goal here with an exponential equation is to solve for the variable in the exponent. So in this particular case, this one's not bad. Straight up, I've got 3 raised to the 2x is equal to 3 raised to the x minus 5. If the bases are equal, what does that imply? Well, the bases kind of cancel, but that actually means that the exponents are equal. The 2x has to be equal to x minus 5, and that makes it easy to solve for. Subtract x from both sides, and what do we get for x? X is equal to -5. A nice, easy answer. But that one was kind of in your face and obvious. See, 3 raised to the 2x equals 3 raised to the x minus 5. The bases are exactly the same. Pretty obvious. What about something like this? I've got 8 raised to the x is equal to 2 raised to the x plus 4. These two bases are not the same. One's a base 2, the other one's a base 8. But what exactly is 8? Here's the trick. 2 cubed. So I can rewrite this as 2 cubed raised to the x is equal to 2 raised to the x plus 4. And reviewing our exponential properties, power to a power, what do I do with the powers? Multiply. This gives me 2 raised to the 3x is equal to 2 raised to the x plus 4. And once again, once the bases are equal, that implies that the exponents, 3x has got to be equal to x plus 4. And then solving for x, I would subtract x from both sides, gives me 2x equals 4, divided by 2, I get x equals 2 is my solution. Does that make sense? Again, those are the nice type. What if you get something that is a base that can't quite get it into? What are you going to do? Well, and in this class especially, being a calculus class, we focus on the natural log. You can use any log you want to. You can use log base 10 if you want to, common log, but we're a science class. And because the natural number, 2.71828, whatever, occurs in nature naturally, calculus is a natural product of the science around us. We focus on the natural log. So you'll see me use the natural log a lot. So a couple of properties here about this natural log. If I have the natural log of b raised to the x, thanks because this is a logarithm, where do exponents get to go? out front, property number 3 that we have memorized from last time. So natural log of b to the x is equal to x times the natural log of b. And the natural log of e to the x. What exactly is a natural log? It is a log base e. And when you're taking it of e to the x, when the base and the exponential are the same, they're inverses, they cancel each other out, and you're left with x. In other words, anytime you've got an e in a problem, you want to take the natural log, because natural logs kill off e's and bring down exponents. That's the real property here. So, look at this first problem here. Solve for x. I've got e raised to the 7x plus 3 equals 5. So, here we go. E raised to the 7x plus 3 equals 5. I've got this e by himself. What kills off e's? Natural log. So we take natural log of both sides. This cancels, leaves me with 7x plus 3 equals the natural log of 5. In real world of natural logs and stuff like that, the nice days of the answer being 2 and negative 3 are long since gone. The natural log of 5 is nothing but a number. You could put him on the calculator if you really wanted to. This stuff I did from last class. Natural log of 5, it's just some crappy decimal. That's all it is. It's a number. Treat him as a number. Now, for you engineers out there, most of you engineers would probably want to replace the natural log of 5 with 1.6094 whatever, and then solve for x, and that sometimes is perfectly fine. The problem that I'm trying to also get you guys to do is prepare for the final exam. The final exam, they may convert the answer to decimals, or they may convert it into simplest terms of exact solutions. I mean this. Solve for x. Treat the natural log of 5 as just as a number, but keep writing them as the natural log of 5. If I want to solve for x, I would subtract 3. This gives me 7x is equal to the natural log of 5 minus 3. And then I would divide both sides by 7, and x would be equal to the natural log of 5 minus 3 divided by 7. This is that back of the book multiple choice kind of answer look to that I'm talking about. So you got to have the ability to do it both ways. Convert it to a decimal as well as leave it in exact value format. All right, look at the next guy. 2 raised to the x is equal to 12. Problem is, let's see here. 2 to the first is 2. 2 squared is 4. 2 cubed is 8. 2 to the fourth power is 16. So I think the answer, since 12 is somewhere between 8 and 16, I think the answer is going to be 3 point something. But I got to have 9 decimal places for accuracy or something like that. So what am I going to do? Well, it's an exponential equation where I cannot write the bases as the same thing like we did up here. So what's the only thing in the universe that brings down exponents? Oh, no, square roots. Square roots kill off squares. What brings down exponents? What's this whole chapter about? Logs. Good. Thank you for studying. Logs, right? This whole chapter is about logs. Logs bring down exponents. That's their whole job in life. When you've got an exponent, a variable in the exponent, and you need to solve for it so you can bring it down to solve for it, you want to use a log on this thing. I can use either common log or natural log. It wouldn't matter. Let's use the common log. I'll show you. If I take the log of both sides, now the reason why I choose either common log or natural log, because I want to have that ability to convert it to a decimal when I need to. Those are the 2 buttons that are on the calculator for calculating not logs. So what I do to one side, I do to the other. That's a perfectly legal math move. However, because I have a log of something with an exponent, where did the exponent get to go? To the front. Property number 3 on log properties we have memorized. So x times the natural log of 2 is equal to the natural log of 12. Log of 2 equals log of 12. Now, here's the deal. Log of 2, nothing but a number. Log of 12, nothing but a bigger, crappy number. I want to solve for x. What are we doing to x? We're multiplying by the log of 2. What gets rid of multiplying by the log of 2? We're going to divide by the log of 2. Treat it like a number, because it really is a number. This cancels. Leaves you with x is equal to the log of 12 over the log of 2. And then if I wanted to calculate the decimal version of that, all I got to do is type in log 12 divided by log 2. And I get what I expected, 3.5 somewhere else, 3.5849625001. And now I got my accuracy that I require. Now, I could have, catch a pattern. A couple of things. Number 1. Can I do this? Log of 12 divided by log of 2, wouldn't that be like the log of 6? Because 12 divided by 2 is 6, and that makes some simple math, right? Wrong. All right, you can't do that. Because, you know, the log of division turns into subtraction, whatever. But the fact of the matter is, this is a special number and this is a special number. You can't just divide what you're taking the log of. This is a number, this is a number. The logs do not cancel. You don't, it's a function, not a number. All right, so, however, I could have, just to show you a pattern, I could have used the natural log. If I take the natural log of both sides, what I do to one side, I do to the other, that's perfectly fine. Exponents still get to pop out front, so I get x times the natural log of 2 equals the natural log of 12. And then, being a number and solving for x, I'm going to divide by the natural log of 2 on both sides, and I get x is equal to the natural log of 12 divided by the natural log of 2. And notice, when I type that in on my calculator, the natural log of 12 divided by the natural log of 2, I get the same answer. Just a different log form. So, you have to have the ability to, okay, I got multiple choice answers. One of my answers was this guy, but it wasn't written as this guy. You should be able to see that they're actually the same thing. All they did was change the log type. All right. All right. There are two different kinds of log equations. So I'm going to throw in an extra example on you guys. So I want you to compare the difference between the two. So this is one I did not type up, but I should have. So here we go. Solve this guy. Log base 2 of x plus the log base 2 of x minus, let's see here, 2 is equal to 3. All right. There are two different kinds of log equations up here. I'm going to call this guy type 1. I'm going to call this guy type 2. What's the difference between the two different types of log equations? Well, no, they're just logs. I can use natural logs on this thing if I really wanted to, and I could have used...
What's type 3, what's type 4?
No, there is no type 3 and type 4. There's only 1 and 2s.
Well, like, you know, I'm talking like pre-calc. Like one has, they're on both ends of the equation, there's an ln or a log.
Okay, now you're getting to it. Look at this equation. This equation has logs on both sides that equal to. This equation had logs on one side, it's just equal to a standard number on the other. That's the difference between two. Type 1, I got all my logs on one side equal to a number on the other side, 3, 5, something like that. Over here, I got logs on both sides. That's the difference between the two. And the reason why I'm showing you this is because the technique you use to be able to solve them is slightly different at the end, depending on the type you have. So let's take a look at type 1 log equations. Type 1 log equations. Anytime you got the logs on one side equal to a number, you want to use this. It's called the definition of logs. Definition. If I have y equals the log base a of x, this is equivalent to what? A raised to the y equals what you're taking a log of, x. It was that smiley face definition that I talked about last time in terms of manipulating logs. But here's the deal. To be able to use this definition of logs to rewrite it, you got to have one log. You remember all those log properties we did? Here's where it shines at for you. To be able to use the definition of logs, to be able to rewrite it, I've got to have one log, which means I need to combine logs. What's the coefficient from my logs in this thing? What's the coefficient from both those logs? Well, understood what numbers right here? Ones. And if you remember our log properties, we need to have ones in front of the logs before we combine them. If there was a number in front of the log, you had to put him back in the exponent from which he came. Since there is a 1 in front of it, this is addition. Addition turns back into what? Multiplication of the terms. X times x minus 2 still equals 3. Now, Here we go. I've converted my multiple logs here to one big log, equal to a number. Now, I'm going to smile at it. Start with the base, use your definition. Raise it to the other side, 2 cubed equals what you're taking the log of, x times x minus 2. Okay? What's 2 cubed? 8. Oh, we can do math. 8. What is x times x minus 2? I'm going to distribute. That's going to give me x squared minus 2x. This should scare you to death. What did my log equation just turn into once I combined logs and then used the smiley face definition to get rid of the log? Quadratic. That's right. I can hide any equation in your entire past in a log equation. Until you smile at it, you won't know what it pops into. But how do you solve a quadratic equation? You got to set it equal to what first? All right. So I'm going to subtract 8 from both sides. 0 equals x squared minus 2x minus 8. If you're real lucky, you're quadratic factors. If not, quadratic formula. Negative b plus minus square root of b squared minus 4ac all over 2a. Yep, you have it memorized too. But I made this problem up so you can bank on it factoring. All right, how does this factor? What times what is 8 that differs by 2? 4 and 2, right? And it's got to be minus on the 4 plus on the 2. You set each factor equal to 0 and you solve. I got x is 4 and I got x is negative 2. However, you are not done. We also had log properties. These log properties keep honing you. One of the log properties was this, about the domain. You can only take the log of positive numbers. You can't take the log of 0, and you can't take the log of a negative number. And just to prove to you, via math on the calculator, what is the log of negative 10? Okay, I have it in complex mode. Let me change my mode so you guys can see. Get back to real math here. Sorry about that. All right. What's the log of negative 10? Non-real answer. Does not exist. You can't take the log of a negative number. Imagine if you could, and we're back to imaginary numbers and complex numbers and stuff. But in real math, which is what we're after, solving real equations, you can't do this. So what I'm telling you is this. When you have any log equation, you have to check your answers. And the reason why is because you may have something called extraneous solutions. You did all the math correctly, but all of a sudden a negative answer or something that officially doesn't solve the equation will pop up also as a solution. And it happens in this problem. I got 4. Go back to the original equation. You're not testing to make sure it works out fine. You should, hopefully your math did well. You're trying to make sure that you haven't screwed up in taking the log of a negative number problem with your answer. Plug in 4. Log base 2 of 4. Well, that's fine, because you can take the log of 4 because it's positive. What's 4 minus 2? 2, and that's still positive. You can take the log of that. So this is a good solution. However, try negative 2. Plug in, go back to the original equation, plug in negative 2. What is negative 2 minus 2? Negative 4. What is the log base 2 of negative 4? And not allowed. So this is an extraneous solution. And you see a lot of them in these log equations. But just don't mark through them because he's negative. That's not what I'm telling you. But you need to test them to make sure you're not taking log of a negative number. Because if I had decided to start with this equation instead of the original one that I gave you, watch this. Plug in negative 2. Negative 2 minus 2 is negative 4. Times that negative 2 makes it positive 8. And now it's perfectly legal to take the log of that number. So it depends on what the equation originally was. You have to go back to the original equation and check your answer. Okay? So with this one, there's only one answer. The x is 4. Now let me. Well, when you go back to the original equation, this is originally what I gave you. Plug in negative 2. Plug in negative 2 for x. That'll be log base 2 of negative 2. You can't take the log of a negative number. But if I had given you this as your original equation, this is what you started out with, then if you plug in negative 2, it actually works out for you. Negative 2 minus 2 is negative 4. When x is negative 2, so it's negative 2 times negative 4, which is a positive 8. Now it's legal to take the log base 2 of it. Okay, so again, check your answers, and always go back to what was the original equation that you started with to check your answers. Okay. What about this guy? The natural log of x plus 2 minus the natural log of 4x plus 3 equals the natural log of 1 over x. You want steps? I give you steps. Step 1, regardless of the type log equation that you have, the first thing you should always do is combine logs. You don't like manipulating multiple logs when you're solving. So you want to work backwards to combine logs. All right. What does subtraction turn into? Division. Notice the coefficients from my natural logs are 1, so this is perfectly legal here. And it would be x plus 2, because that's the positive guy, divided by 4x plus 3 equals, and on the left side there's only one term, the natural log of 1 over x. But look at this property up here that I gave you. It's a log property. If log base b of m is equal to log base b of n, then m has to be equal to n. Kind of works from that same exponential property that we had when I had b to the m equals b to the n. If the bases are equal, the exponents are equal. Here's the deal. If the logs are equal, then what you're taking the log of have to be equal. The way you need to look at it is like this. I've got the natural log of garbage equals the natural log of garbage. If they've got natural log of garbage equals natural log of garbage, then the two garbages have to be equal to each other. You're not... Well, officially you can call it canceling the natural log. Do not do this because it just frustrates the math. It'll get you the right answer, but it's not mathematically correct. I'm not going to divide by natural log on both sides and cancel out the natural logs because natural log is a function, not a number that you just divide by. Does that make sense? So it's called canceling the function. If the natural log of garbage is equal to the natural log of garbage, then that implies that the two parts, the garbages, have to be equal to each other. So I have x plus 2 divided by 4x plus 3 equals 1 over x. You're canceling the natural logs is what you're officially doing. Does that make sense? Now, what did it turn into? Rational function. How do you solve a rational function? How do you solve a fraction equal to a fraction? What are you going to do? Ah, good. Cross multiply. So I'm going to do this cross multiply. That's going to give me x times x plus 2 would be equal to 1 times 4x plus 3. And I wrote it like this so you guys can see when you go back and review this that I'm actually cross multiplying. Get rid of the denominator. Now I'm going to distribute to get rid of my parentheses. I got x squared plus 2x equals 4x plus 3. What did it turn into? Oh, no, not again. So what do you got to do? Set it equal to 0. By the way, the reason why I did this is because Weber loves quadratics and fractions and stuff. Okay, so this cancels. So I get x squared, 2x minus 4x is a minus 2x minus 3 equals 0. It is going to factor, or you're going to have to use the quadratic formula. Does this thing factor? How does it factor if you believe it factors? X, 3 and 1, minus on the 3, plus on the 1 equals 0. X minus 3 equals 0. X plus 1 equals 0. That means x equals 3. X equals negative 1. Does that make sense? Now, here's the deal. Are you done with this problem? No. You are not done with this problem. You have to, it's a log equation. You've got to check your answers. So, check 3 and go to the original equation and plug in 3. You're not checking to see if it's right. You're checking to make sure you're not taking a log of a negative number, which violates the rules of math. 3 plus 2 is 5. That's nice and fine. 4 times 3 is 12, plus 3 is 15. Nice and fine. 1 over 3 is a third. Still nice and positive. 3 works. What about negative 1? Watch this. Negative 1 plus 2 is 1. 1 is positive. That's the legal move. 4 times negative 1 is negative 4 plus 3 is negative 1. You can't take the log of negative 1. That makes this an extraneous solution.
What do you distribute the negative sign?
What do you mean? No. Okay, we're up here? Nope, not allowed. This is a function, not a parentheses, not a number. You can't distribute. It's like the cosine of 4x plus 3. It's the same idea. This is the angle part. You can't touch this. It's on as part of the inside of that natural log function. Yes, ma'am.
So if it was 3 it would go through to that point, right?
Yes, it would.
But it could, if a negative number could never be,
Well, then I would have issues, exactly, then I would go here. But once it failed on one term, I don't care about the rest of them, I'm done.
is it always gonna be if it's 1 over x, and if it's negative, I mean,
No, that's gonna be a problem, yes.
yeah, okay.
Okay, but, I mean, you really have to check on each term and stuff like that. So I just go typically from left to right, and that was the first term that I came across that it actually failed. Therefore, I don't care about the rest of them. But yeah, you're right, it fails this one too. Whenever -1 is -1, can't take log of that either. Okay? So, let me explain something to you. What they're going to do to you on the final exam, which means I must do it to you on the test to get you guys prepared, as well as the homework. This is what I do. Multiple choice part. You know what they're going to do. Either one of these two problems. They're going to give you A, the answer is 4. B, the answer is -2. C, the answer is 4 and -2. C, the answer is no solution. E, we got to make up something. The answer is 45. Okay. That's what we make up answers to kind of put in here. But notice the rest of them. You would be amazed how many people tell me the answer is 4 and -2. Because when they did everything right, that's what they got, and they circled the answer and they moved on. And they forgot the biggest thing about logarithmic equations, which is check your answers. Plug it in and make sure you're taking log of positive stuff. That is a common mistake. Then because it's so common, they like to put that on the final exam to make sure that you know your algebra stuff. Separate those A's from B's type people. And C's and D's and F's. Yeah. But okay. And the same idea on this one. Answer A is -1, B is 3, C is 3 and -1, D is no solution. And no solution is possible too. What happens if they both don't work? No solution then.
Just take the answers and plug them in and see if they work.
Well, yes and no. I mean, you could officially do that, but what's going to happen when you get to the word problem part? Because you understand, this is just setting up the equation type thing here. I'm just trying to get you guys to double check that where the common one is, they always make that C, -3 and -1. And sometimes both of them work, but you got to check all of them. I mean, you got to check your answers and stuff like that. But later on, what are we going to do to this stuff? We got some kind of interesting flowing out of a tank, and the function that it happens to deal with is a natural log function. And you're going to take the root of that sucker and then set him equal to 0 and solve, and you're going to have all kinds of problems. But this type of stuff will continue to haunt you. All right. Next guy. Yes, ma'am.
Is there, like, a time whenever those won't be equal to each other? Like where you cross multiplying?
What do you mean, over here?
Yeah, are those always gonna be equal to each other?
Well, when you combine logs on this side and combine logs on this side, I mean, it could be instead of a division, it could be a multiplication or something like that. But yes, on type 2 equations, once you combine logs, you'll have a log of something equals a log of something. You cancel the logs, and then you get the two somethings equal to each other. And it could turn into a quadratic. You could cross multiply. It could be some kind of weird fraction thing. And there's lots of different ways.
Ever have different bases or something like
Good point.
equal to each other?
Exactly. In terms of logs, you can only combine like terms. So they have to give you the same type of log. And if they don't, then you're going to use the change of base formulas to turn them into the same log so you can combine them. You got to have the same log. So 99 times out of 100,
Will there be one like that in the past?
they're always going to give you the same logs. They're not going to give you different logs. This is natural log of x plus 2 is equal to a common log of 4x plus 3 minus log base 2 of 17x. But no, they wouldn't do that to you. But what's your major?
Bio.
Biology. All right, in biology, you're going to see a lot of the natural log stuff because of that population growth and decay. But you also see a lot of common log, pH balance stuff. They always use the common, negative log of the positive hydrogen ions equals the pH stuff. You remember that formula. So you guys tend to use a lot of different kinds of logs, and especially natural logs for your exponential and growth and decay type problems, as well as the common logs for your pH kind of problems. But if you notice that when you're working in one world, they always play with the same log. When you're doing pHs, it's always the common log. When you're doing those exponential growth or decay or radioactive stuff, it's always the natural log. So there's still that sense of focus, and they're always going to give you the same type of log. All right, number 4. Solving for variables in the exponent. See, here's the deal. When it comes to log equations, I have domain restrictions. I can't take the log of negative numbers, nor can I take the log of 0. But when it comes to exponential equations, your domain on an exponential equation is all real numbers. You can have negative exponents, you can have 0 exponents, you can have positive exponents. So when it comes to an exponential equation, you don't have domain restrictions. All right, solve for the variable in the exponent. All right, so in this problem here, we want you to solve for x, and I would have stated that in the problem. Solve for x. And this is kind of like manipulating formula type stuff here. I want you to solve this thing for x. I got r equals 25 times e to the 38 times x. Now, where is the x located at? It's in the exponent. There's only one thing in the universe brings down exponents. What's that? Logs. And because this thing has an e in the problem, what log would you choose? Natural log. However, try to get you guys to understand this stuff, and this type of stuff works for you, so here comes my twist of math here. Think of E as the enemy. You need to kill this guy off. There's only one thing in the world that kills off E's. What's that? Natural logs. But if you've got to kill somebody off, you need to isolate your victim. Think about this. This really is mathematics. There's some guy blocking your shot. He's got a 25 in front of this thing, right? So what's the first move I got to make to get that E by himself? Divide by 25. Get the E term by himself. I get r divided by 25 is equal to e to the 38x. Get the e by himself, because the property that we have that you're going to use is this. The natural log of e to the x is x. The natural log has to be right beside the e to the x, so the inverses so they can cancel, so you get x out of it. So you got to get the e by himself. Now, once I got the e by himself, I'm going to take the natural log of both sides. Perfectly legal. What I do to one side, I do to the other. And the natural log of the e cancel, leaving me with the natural log of r over 25 equals 38x. Now, how would you solve for x? What would you do? Divide by 38. Didn't say these answers are going to look pretty, but this is traditional manipulating math formulas, so they're not going to look pretty, but they are formulas to solve for the variable that you want. So there you go. So I get the natural log of r divided by 25 divided by 38. That is my solution. Does that make sense? All right, take a look at this next guy. Again, for these equations, I want you to solve for x. I got y equals 8 times e to the t times x. Your focus is on x. Solve for the x in the variable here. So, it's got an e in the problem, and the variable is located in the exponent. You with me? So, what's your first move? Outstanding. Divide by 8. Get the e by himself. Y divided by 8 equals e to the t times x. Remember, x is the variable. Now, once you got the e by himself, what are you going to do? Natural log both sides. So, take natural log, natural log. This gives me natural log of y divided by 8 is equal to, and the natural log and e cancel, t times x. Solving for x, you're multiplying it by t, so what are you going to do to get the x by himself? Divide by t. And I get my solution. X is equal to the natural log of y divided by 8 divided by t. But I should have pulled it over there, sorry. However, what can they do to you on the multiple choice part of the final exam, as well as what can I do to you on the multiple choice of my tests to mess you up on this one?
Y equals ln x over 8?
No, not y equals. I didn't. We had to solve for x here.
Not give E.
No. I could have given you something else besides an e. So you would use either natural logs or common logs, because it would have just killed them off, because bring down the exponent, and you're left with this term over. This is the way they could have also written it: the natural log of y minus the natural log of 8 divided by t, and put that as the multiple choice part of your answers.
You wouldn't do it, so you would subtract the t away from it?
Nope.
Okay.
Because of this. It's a good question, but let me explain what you should be looking at. I've got the natural log. Where's the fraction at? Y over 8. t's not part of that natural log. He's just divided by t whole thing here, right? That's where your fraction is. And you're right, I'm using a log property. That division turns into subtraction. So if they didn't write this as the answer in terms of my part A, B, C, D, multiple choice guesses here, they could have written it like this.
So that Humpty Dumpty the answer.
Yeah, well, pretty much. Either you can put them back together again or break them apart. But I can't guarantee you what the people the department committee who makes up the final exam, what they're going to do to these answers to try to fool you into trying guessing something else. Okay?
Now,
Yeah.
the ln was out front, so it was ln y over a over t.
Yeah.
Then you would,
Then I would do natural log of y minus natural log of 8 minus natural log of t. Because then the t would have been inside what you're taking the natural log of. We're not taking the natural log of t. He's stuck on the outside. All right. Here we go. Basic graphs. So let me get a piece of paper out here so you guys would understand what's going on here. Exponential graphs all look the same, the general shape of it. It's kind of like this. When I tell you guys, hey, what does a quadratic graph look like? Quadratic graph, what does it look like?
Smiley face or frown face?
Okay, well, what do you call that? It's got a name. Parabola. We're not going way back to the 8th grade, but okay, close enough. All right, it's a parabola, U-shaped up or U-shaped down. Be a little more technical on your terms here, but okay. But you understood what that meant because ever since the 8th grade, you've been beating those kind of graphs to death. So when you think of parabola or a quadratic, you know you're thinking about that U-shaped graph, right? Exponential graphs should be the same way. So as long as the base is greater than 1, the exponential graph y equals a raised to the x looks the same. It always passes through 1, it horizontals out on the left and blows up on the right. This is what an exponential graph looks like. We call this an exponential growth graph because as x gets bigger, y gets exponentially bigger. But as x goes negative, this thing horizontals out to 0. There's an asymptote, a horizontal asymptote on the left. And so as x goes to negative infinity, the exponential graph actually goes down to 0. Okay? However, if your base is a fraction, and you have y equals a raised to the x, it would look like this. A complete reflection across the y-axis of the graph. We would call this a decay graph. So when you want a decay graph, you want your base to be a fraction, somewhere between 0 and 1, because that's going to make, as x gets bigger, the amount gets smaller and smaller and smaller going towards 0. Does that make sense? This is a decay graph. This is a growth graph. The relationship between the two is this. The fact of the matter is that this graph here is the same thing as, remember, it's a fraction. So you can also view this as if a was greater than 1, it would be a to the negative x. Would be the same thing as a to the x when a is a fraction here. Let me explain why. We do with negative exponents. Rules of exponential properties here. Negative exponent goes where? On the bottom. You know, you got x to the negative 3. That's 1 over x cubed. You've done many of those problems when I asked you to take all those derivatives and stuff. Well, it's the same idea. When I have a negative exponent, it literally puts the stuff on the bottom or makes fractions. Also, a negative, when you put a negative compared to the x, that's a reflection across the y-axis. That's the way why it is what it is. All right? So, you have this, and we're going to focus on this particular one because there's our standard graph right here. If I have y equals the log base a of x, what does that graph look like? Well, it goes to the point 1, 0, blows up this way, and goes straight down this way. So here's your y-axis, here's your x-axis. And again, a would be a base bigger than 1. So you've got this guy here. Why are these two pictures like the way they are? They are inverses of one another. And what was the relation on inverses? You have this y equals x-axis that splits it right down the middle. And on the y equals x-axis, the inverse is a reflection of that graph across the y equals x-axis. So this point comes over here at the point 1, 0. This part shoots down this way. It actually shoots this way. This part shoots up, so it shoots over this way. And you've got to try to get that reflection thing that was going on here. This is what the log graph looks like. And notice, you can't take the log of a negative number. Doesn't exist.
So there's no reflection for the graph on the right?
Well, yes, there is one. You can actually have, if the base was negative, you could reflect that about this line right here. And then it would end up looking something like, let's see here. This part goes down this way, so it'll have to go up this way. This part goes over here, so we go like down that way. So it's symmetric. But you typically don't use logs with fractional bases. You could, but we don't do that as much. It's log base e, log base 10. E is 2.718, number bigger than 1. Base 10 is obviously 10, so forth and so on. So those are your basic ideas. And again, I am trying to treat this as a review, but that's what this is all about. So I decided to show you the relationship between an actual base, 2. This is what the exponential function y equals 2 to the x looks like. This is what the log base 2 of x looks like. And they are inverses of one another because when I put them on the same graph, they're symmetric about that y equals x-axis. So, also, again, as a tying all this stuff together right here at the end, if f of x equals a to the x and g of x equals log base a of x, then f of x and g of x are inverses of one another. And if you notice a of x, which is this graph right here, the domain is all real numbers. No restrictions. Negative infinity to infinity, if you want to write them like that. Okay? However, what is the range? The range of the y-coordinates. You only get y-coordinates above 0. That would be from 0 to infinity. Y's are greater than 0. But if you look at the graph f of x equals log base a of x, what is the domain? The domain is numbers bigger than 0. X is greater than 0. But the range, remember, this thing goes straight down. So that's from negative infinity up to positive infinity, all real numbers. Negative infinity to positive infinity. And you'll notice that the domain of the exponential becomes the range of the log, and the range of the exponential becomes the domain of the log. Back, reversing. Now, that being said, I want to show you a problem that the calculator has. Okay, y equals, let's graph a log function. Let's do natural log of x. Let's graph it. Zoom 6. That's what it looks like. And a lot of people tell me it stops right there. Does it stop? No. But actually on the calculator it does. Let me show you. I'm going to go to Window. I'm sorry, Format, excuse me. Go to Format. I'm going to turn my axis off and then graph it. So it just graphs the picture without the axis on there. And what does it do? It stops. But in reality, it actually keeps on going straight down. Why doesn't the calculator tell me it's going straight down? Why does it stop? Because this is a functional calculator. And if it goes straight down, it's getting so close to the same coordinate on the x that the same pixels are being highlighted. And a function can't do that because it wouldn't pass the vertical line test. So it stopped it right there. Okay? The calculator can't draw vertical lines as functions because it's randomly plotting points is what it does. So you have to outthink the calculator. This calculator will stop, but you better know, being a log graph, actually it continues going straight down vertically. Okay? Now let me do this. Format, put my axis back on. There's my axis again so you can see the graph again. All right. So, knowing all that, answer these last few questions, then we'll go on into chapter 3.1, 3.2 from a calculus perspective and doing limits. Find the domain and range of this function right here. On your mark, get set, go. F of x is equal to the log base 5 of x. Well, I can read you right now. What is the domain? It is 0 to infinity. I would also accept x is greater than 0, but WebWork wants this because it's an interval notation, because you can't take the log of a negative number and you can't take the log of 0. What's the range? Always. All negative infinity to infinity. All real numbers. The range of all log graphs are going to be negative infinity to infinity. Okay? All real numbers. But then they're going to try to mess you up. Here we go. And what you should do is graph this thing. It's a log graph. We know it goes to the point 0, 1, shoots straight down this way and straight over this way. This is y equals the log base 5 of x. Now the question is this. What is the domain of this new function over here? F of x equals the log base 5 of x minus 4 plus 2. Well, first off, what is the relationship between these two guys? Well, we did some manipulations. What manipulation did we do? What is this x minus 4 going to do to the standard log base 5 of x graph? All right, so this right here is telling me shift right your words. How many units? 4 units. And what is this thing outside telling me? Plus 2. We're going to shift it up 2 units. So what's my picture going to look like? I'm going to take this picture, shift him right 4 units. 1, 2, 3, 4. And I'm going to take this graph and shift him up 2 units. Okay? So this is my picture. All I did was take this guy and shift him to the right 4 units and shift him up 2 units. Now I ask you the question. What's domain?
X to infinity, I mean 4 to infinity.
All right. It is parentheses 4 to infinity, because you don't include the 4 because you never touch it. Another way you could have done that was, remember the rule. You can't take the log of a negative number. What are we taking the log of here? X minus 4. It's got to be strictly greater than 0. So when you solve, x has got to be strictly greater than 4. That means 4 to infinity. What's my range? Always. Negative infinity to infinity. Does that make sense? It's going straight down, it's going up. Sometimes they get a little more complicated. So I try to throw out one that's not quite as simple to manipulate. What about this guy? The natural log of x squared minus 1. Well, the first thing is this. In terms of domain, the x squared minus 1 has got to be strictly greater than 0. How do you solve this? Well, if I was doing it by hand, this is a quadratic inequality. I would still factor them. X squared minus 1 factors x plus 1, x minus 1. I'm going to pretend like it's equal to 0 and solve. I get x equals negative 1, x equals 1. I'm going to draw a number line and put these numbers on my number line, negative 1 and 1. The negative 1 and 1 is where the function actually equals 0. Do I want that in my solution set? Yes or no?
No.
No, because it's not equal to on the original inequality. So these will become open circles. You should remember this from Algebra 2 high school. Here's the deal. When I'm solving a quadratic inequality, once I figure out where it's equal to 0, I now put it on a number line and do test values. Pick a number less than negative 1. I choose negative 2. Plug it into the original function, which is x squared minus 1. Negative 2 squared minus 1 is 4 minus 1, which is 3. I don't care what the number is. What kind of number is it? It's a positive number. So we put little pluses here. Pick a number, use your brain, between negative 1 and 1.
0.
Good choice. X is 0. This gives you, when you plug in x squared minus 1, 0 squared minus 1 is negative 1. It's negative. That means that you can't even take the log of that part, because you can't take the log of a negative number. And so what about a number bigger than 1? I choose 2 because I have a brain. Plug in 2 into x squared minus 1. This is 2 squared minus 1, which is 3. It's back to positive again. So what is my domain? Negative infinity up to negative 1, union 1 to infinity. That is the domain. What about the range? Well, if you don't believe my domain, Probably won't believe my range either, but here we go. If you're not sure, graph him on your calculator. Natural log of x squared minus 1. I got a question for you. It stopped right there. Does a log graph just stop? No. What does it do? Keeps going vertically. It goes straight down. So it does this. Okay? So, what is my range? Thing keeps on going up, bigger and bigger and bigger. Keeps going straight down. So what is the range? All real numbers. Negative infinity to infinity. There you go.
Check the element, x squared minus 1 you guys.
Oh, I hit the natural log button right there below the log. All right. This is a large chapter in chapter 3.1, 3.2 because of all the algebra review. The old textbook, what they used to do was just have an algebra review section, and then when you got to chapter 3, you just did the logs and derivatives and the limits and the derivatives and all that good stuff. But in the newer editions of the book, they have gone back and merged together the review section with the calculus section, so they wanted you to review instantly when we were doing this stuff, not at the beginning of the class and the review chapter for the whole thing. So, here we go. We're in the calculus part. So I'm still in chapter 3.1, but now we're going to talk about calculus, and the calculus that we're referring to is the limits. We'll get to the derivatives in the section 3.3 in just a second here. All right, so rule